Something is awry in the early universe and scientists have no idea about it.
Already in the very early data we obtained nearly 2 years ago. And I think the surprising thing was that it's actually very bright. And so our initial reaction was that, well, it cannot be that distant.
Sometime after the Big Bang, around 12+ billion years ago, when the universe went from a dark, diffuse place full of gas to a light-filled universe populated by stars and galaxies. This is the era that laid the foundation for everything to come, including our solar system and you and me. Scientists had some theories about what happened during this crucial period, but James Webb is giving us a new dictionary to translate the language of the early universe. What James Webb found is too different to fit scientists' current theory of how the universe grew up. This has raised some concerns that the history of the early universe needs to be rewritten.
Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe.
Join us as we dig deep into how James Webb just cracked the universe's code. Over the course of the past century, astronomers and physicists have produced an incredibly rich and detailed account of our universe's history. This picture, sometimes called the Standard Model of Cosmology, sometimes called the Inflationary Hot Big Bang, and sometimes called the Lambda Cold Dark Matter Model, has been remarkably successful. This model, initially developed in the early 20th century, has survived a battery of observational tests and is extremely good at explaining a variety of cosmological observations, including the redshifting of light from distant galaxies, the appearance of leftover radiation in the form of the cosmic microwave background, the abundances of light elements, and the evolution of galaxies and larger structures. While the Big Bang Theory can't say for certain which galaxies will appear where, it can talk about probabilities. It predicts that, as we look farther and farther back in time, that is to greater and greater cosmic distances, that the galaxies we see will be inherently smaller, bluer, less evolved, less rich in heavy elements, and that at some point, beyond where we've been able to look, we should cease to see stars or galaxies of any type, as we'll reach the universe's dark ages. But that's simply a picture of what happens. What we need, if we want to compare theory to observations, is to quantitatively figure out not just what happens, but when it happens, and, quantitatively, how much it happens by. Even though the laws of physics are well known, and the starting point, or our initial conditions, are also well known, our best quantitative predictions still come along with a large amount of uncertainty. From the theory of cosmic inflation and the patterns of fluctuations that we see in the cosmic microwave background, we know that our universe began at the start of the hot Big Bang from an almost perfectly uniform state. There were the seeds of structure, density imperfections, imprinted atop that near-uniform background, leading to underdensities and overdensities at about the 1 part in 30,000 level, that were almost but not quite the same on all cosmic scales. About 3% larger on size of the universe scales than on size of a galaxy scales. We know that early on, these imperfections grew gravitationally, but also had to contend with interactions with and pressure from radiation, like photons, creating a pattern of peaks and valleys in how overdense, underdense various regions were on a variety of cosmic scales. Then, the universe forms neutral atoms, about 380,000 years after the hot Big Bang, and expands, cools, and gravitates according to the laws of general relativity. As long as these density imperfections remain small compared to the average density of the universe, it's easy and straightforward to compute how they grow. But as they grow larger, a series of effects all come into play, making the question of how big do they grow and how quickly very assumption dependent. For example, as large amounts of gas begin to accrue in these overdense regions, how efficiently does that gas cool? As these overdense regions grow within the expanding universe, with some small-scale regions superimposed atop larger-scale overdensities. How do these high-density regions interact in these overlapping locations? Some overdense regions will occur close to other overdense regions. How is the growth of structure affected when these regions interact? As normal matter accumulates in the centers of these overdense regions, it slows down, collides, and heats up. As that heat gets radiated away, how does that feedback affect the growth rate of these regions, including both the normal matter and the dark matter? And finally, when stars finally form in these very different environments to the ones we find today, how long do they live? How do they die? How does that impact the normal and dark matter that doesn't become stars? And what implications does that have for subsequent generations of stars and the growth of these early cosmic structures? It's important to understand that the answers to all of these questions are uncertain. They're firmly in the realm of the purely theoretical and are dependent on what details we include and exclude in our models and simulations. Are we using the correct models to identify halos, where a halo represents an individual overdensity in space, or are we incorrectly treating interdependent halos as independent entities or vice versa? Are we modeling the first stars correctly, including their initial mass functions and their death throes, or are they heavier and more likely to directly collapse to black holes than we think? For that matter, do we even need stars to form black holes? Or can these intersecting, inflowing streams of gas form the seeds of supermassive black holes directly, possibly with masses that are millions of times the mass of our sun right away? It's pretty clear that the very first objects, stars, black holes, and star clusters, begin forming no later than about 150 million years after the Big Bang, and perhaps as early as only 50 to 100 million years after the Big Bang. But these ought to be relatively rare occurrences. But now, for the first time, owing to the unprecedented capabilities of the James Webb Space Telescope, we're beginning to discover and characterize unpredicted ancient objects found in these very, very early stages of our cosmic history. But why is the James Webb Space Telescope so good? The short answer is that James Webb is optimized to see in the near and mid-infrared. As light travels towards us from faraway objects, it gets stretched into longer wavelengths, redshifted, due to the expansion of the universe. The light we see from a star near the beginning of the universe took billions of years to reach us. It may have started as ultraviolet or visible light, but by the time it reaches us, it's near and mid-infrared light. So, to see the early universe, we need a telescope like James Webb. Its infrared capability also allows us to peer into dense dust clouds shrouding newly forming stars, giving us an inside view like never before. However, right from its first observations, the Webb telescope has given astronomers new puzzles to solve and new questions to pursue. In particular, it is challenging what we thought we knew about the early evolution of galaxies. James Webb's intriguing deep-field observations of faint light from the early, distant universe reveal stars and galaxies that seem to be much larger than expected. The SEERS, Cosmic Evolution Early Release Science Survey, led by Prof. Steven Finkelstein of the University of Texas at Austin, used James Webb's NIRCam instrument to look back as far as the epoch of reionization, just after the so-called Dark Ages of cosmic evolution, to study the structure of galaxies in the very early universe. It found more of them than predicted, and they appear bigger and brighter than expected. According to our best models of how the infant universe developed, they aren't supposed to be there so early or look as they do. Some of the first survey results have even indicated there are mature-looking disk galaxies reminiscent of our own Milky Way present as early as 10 billion years ago. We were expecting a more chaotic picture, with predominantly irregular galactic structures interacting violently. James Webb's advanced resolution, coupled with its ability to observe very distant early objects in infrared, has made us think again about how soon galaxies began to form and mature. These findings challenge our current understanding of how the early universe developed and pose some fascinating questions. Were the properties of stars and galaxies in the infant universe dramatically different to now? Might the rate of star formation have been faster and more efficient in the early universe? Could the light from these early objects have been emitted in a way we've never seen before, because the chemical composition of the early universe was different? What does this mean for our best theoretical models of galaxy evolution? Disk galaxies like our own may be where life could develop in the universe, and we're finding them much earlier than we thought. Follow-up observations are ongoing with larger datasets, complementary observations from other telescopes, and spectroscopic analysis from JWST's NIR-SPEC instrument to refine these early results and seek answers to the questions they have provoked. As Christopher Consolis, Professor of Extragalactic Astronomy at the University of Manchester, UK, and a Sears co-investigator said, "Using the Hubble Space Telescope, we thought that disk galaxies were almost non-existent until the universe was about 6 billion years old. But these Webb results push the time these Milky Way-like galaxies form to almost the beginning of the universe." The discovery of unexpected galaxies doesn't end here. Dr. Tim Carlton and a team at Arizona State University have been working on another James Webb Survey-duted pearls, or prime extragalactic areas for reionization and lensing science. As part of this survey, James Webb's NIRCam has picked out an anomalous dwarf galaxy 98 million light-years away, in an area where the team wasn't expecting to see anything. Even more interestingly, its behavior doesn't seem to fit with our current theories of galaxy evolution. Dwarf galaxies are common enough, but this one isn't doing what we might expect. We would expect to see a galaxy like this interacting gravitationally with a bigger companion galaxy nearby, or actively forming new stars, or both. This one, dubbed Pearls DG, is doing neither. It's all alone and its stars are old, challenging our understanding of how galaxies work. It raises the prospect that there could be many more of these anomalous galaxies out there, not doing what we expected, and we haven't been able to detect them until now. In addition, the Webb telescope has also been adding to what we know about the rate of the expansion of the universe. Back in 1929, the American astronomer Edwin Hubble presented the first observational evidence that the universe is expanding in all directions. Hubble proposed the Hubble constant to express the rate of this expansion. Astronomers have known since the 1990s that the rate at which the universe is expanding is increasing, but can't explain why. Explanations to account for this include the mysterious forces known as dark energy or dark matter, but perhaps it's some sort of unknown particle we don't know about yet. Numerous investigations have been undertaken to work out the nature of these unseen components of the universe. Cosmic acceleration can be measured by the distance of objects in the nearby universe and how fast they're moving away from us, or by measuring fluctuations in the cosmic microwave background, heat left over from the Big Bang, linked to the density of matter in the early universe. You'd expect that these two methods would agree with one another, but instead, measurements of the distant early universe suggest a slower rate of expansion than measurements of the nearby, more recent universe. The rate of expansion seems to vary depending on where you measure it. This is called the Hubble tension, and some have gone further and dubbed it the Hubble crisis. We need the Hubble constant to confirm the age of the universe definitively and even predict what might happen in the future. This is a big deal for cosmologists. To put a number on the current expansion rate, we traditionally use measurements of Cepheid variables. These are massive, pulsating stars 100,000 times brighter than our Sun that act as useful distance markers in space. Hubble has been making observations like this in our nearby universe for decades, but there had been speculation that undetected measurement errors might be growing more pronounced as we looked deeper into the universe. Was crowding by other stars and dense dust clouds in the early universe impacting the accuracy of more distant Cepheid luminosity and distance measurements? Maybe this, or something like it, could explain the apparent discrepancy of the Hubble tension. Enter the James Webb Space Telescope and the S80ES team led by Adam Riess at Johns Hopkins University. Prof. Riess co-won the Nobel Prize for Physics in 2011 for the discovery of cosmic acceleration using data from the Hubble Space Telescope, and he and his team have used James Webb to cross-check the Cepheid variable measurements across the whole distance range of Hubble's observations. With its enhanced precision to pick out Cepheids from other stars and its ability to see through the thick dust clouds obscuring them, James Webb has confirmed definitively that the Hubble photometric observations of the Cepheids are correct. We can now rule out a systematic measurement error. So, what else is causing the Hubble tension? There is the very real and rather thrilling possibility that we need some new physics to explain it. To assist with these new ideas, missions like ESA's Euclid and NASA's Nancy Grace Roman Telescope will conduct wide-field surveys to tell us more about the influence of dark energy on expansion. Roman is due to launch before the end of the decade, with a field of view 100x wider than Hubble. One of its objectives will be to study how the distribution of galaxies and dark matter has changed throughout the history of the universe. Meanwhile, Euclid launched in July 2023 and is already exploring the composition and evolution of the dark universe on a cosmological scale. Like a cosmic version of Google Maps, Euclid will provide astronomers with the most comprehensive three-dimensional inventory of the universe ever. What ESA's Gaia mission, launched in 2013, did for the majority of stars in our Milky Way galaxy, Euclid will do for a huge number of galaxies in the wider universe, precisely determine their position on the sky, their shape, and their distance. How will it do this? Well, a galaxy's distance follows from its so-called redshift. The longer the light from a galaxy has traveled through expanding space to reach our telescopes, the further the light waves are stretched to longer wavelengths, corresponding to a redder color. For the 25 million brightest galaxies observed by Euclid, the redshifts can be directly measured from the spectra obtained by Euclid's near-infrared spectrometer and photometer, or NISP. For 1.5 billion fainter and more distant galaxies, for which no detailed spectra are available, Euclid's near-infrared measurements are combined with at least 4 brightness measurements at various optical wavelengths, obtained by existing large ground-based telescopes such as the Canada-France-Hawaii Telescope, Subaru Telescope, and Pan-STARRS, all in Hawaii, and by the future Vera Rubin Observatory in Chile. From the resulting spectral energy distribution, astronomers can deduce a photometric redshift, albeit less precise than NISP's results. As Euclid's project scientist René Lorais at ESTEC explains, mapping the three-dimensional distribution of galaxies at different redshifts sheds light on the cosmic expansion history. After all, the current large-scale structure of the universe evolved from primordial density perturbations a few 100,000 years after the Big Bang, which have been mapped in detail by ESA's Planck mission. Measuring how the large-scale distribution of galaxies has changed over time will tell astronomers if and how dark energy has also evolved. Of course, to study the role of dark energy in this way, you have to take the existence and spatial distribution of dark matter into account too. That's where the razor-sharp images of Euclid's camera operating at visible wavelengths, also known as VIS instrument, come in. Dark matter doesn't emit any form of radiation, but it betrays its presence by slightly distorting the shapes of background galaxies in a process known as weak gravitational lensing. According to Albert Einstein's general theory of relativity, light is bent by concentrations of mass, whether visible or dark. In other words, a concentration of mass will reveal itself through weak lensing. Thus, a statistical analysis of the shapes of millions of background galaxies at various cosmological distances makes it possible to reconstruct three-dimensional maps of the mass distribution in the universe. In studying weak lensing, the Euclid mission will in fact map local deviations from the average large-scale geometry of the universe, so it's quite appropriate that the mission has been named after Euclid of Alexandria, the father of geometry, who lived in the 3rd century BC. In addition to mapping the distribution of dark matter and revealing the expansion history of the universe, Euclid will also measure a parameter known as gamma, which describes the growth of structures like clusters of galaxies. If this parameter doesn't match predictions from general relativity, that would support alternative theories of gravity, like MOND, for modified Newtonian dynamics. With MOND, you pretty much get what's on the label. At planetary or solar system scales, Newton's gravity works just fine, of course, except where you need the more detailed calculations of gravity provided by general relativity. But once you go big, the usual F equals ma we're familiar with doesn't quite apply, and the relationship between force and acceleration follows a different rule. Under MOND, there's no need for an additional particle to explain the observations, just a slight tweaking of the gravitational force. And because the tweaking of gravity under MOND is explicitly designed to explain the motions of stars within galaxies, it naturally does that very well. The theory also doesn't suffer from the overproduction of satellites and the extremely high galactic cores of dark matter. But MOND is far from perfect. The modifications made to gravity to explain stellar motions have trouble explaining the motions of galaxies within clusters and the lensing of background light. And MOND isn't a fully relativistic theory. All modern theories of physics must be compatible with special relativity. An update to MOND that is equivalent, called TVES, can compete head-to-head with general relativity and falls far short. Models based on modified gravity have significant trouble explaining the growth of structure in the universe, features of the cosmic microwave background, and more, all places where dark matter works quite well. There is no MOND-like theory that can account for every single observation when it comes to dark matter. All of them fail at least one test. While MOND may still be accurate when it comes to galaxy rotation curves, there are enough observations to tell us that we would still need dark matter to exist in the universe. No, the dark matter hypothesis isn't perfect, but then again, no scientific hypothesis is. When evaluating competing hypotheses, scientists can't just go with their guts or pick one that sounds cooler or seems simpler. We have to follow the evidence, wherever it leads. What's notable, scientists working on CERN's Compact Muon Solenoid (CMS) experiment have published the latest data in their search for a long-lived exotic particle known as the dark photon. Dark photons, also called hidden photons, differ from regular photons, particles of light, in that they are thought to have mass, making them a prime candidate to explain dark matter. Dark matter, as told, is the catch-all term to describe seemingly invisible stuff in space that has only been observed via its gravitational effects. But it has never been directly detected, and no one is sure what it actually is. Physicists at CMS are trying to change that. Like particles produced in other experiments at CERN, the hypothetical dark photons would be produced by the decay of another particle, the Higgs boson, which was proposed in the 1960s and famously observed in 2012. Higgs bosons are thought to decay into dark photons, which then would decay into displaced muons. The CMS collaboration is working to constrain the parameters at which that process would occur. CERN's Large Hadron Collider began its third run in July 2022, with a greater capacity for particle collisions than in its previous runs. This means that the CMS experiment's algorithm, or trigger, which detects interesting collisions, has more events to sift through, and thus more opportunities to spot displaced muons that resulted from dark photons. Dark photons are considered long-lived by particle standards. They exist for 1/10 of a billionth of a second. Despite their longevity, they are difficult to spot, which is why no one has done so yet. In fact, the search for dark photons has been going on for years. As physicist James Beecham said, dark photon searches are simultaneously straightforward and challenging. Straightforward because the concept is general and simple enough that designing experimental searches is pretty easy, but challenging because we really have no clue where in the parameter space the dark photon could live. Some scientists are looking for dark matter using little mirrors, while others are trying to tune into its frequency with a dark matter radio. At CMS, physicists are trying to spot the particles as they decay into muon pairs. In a boost for CMS, the Large Hadron Collider will soon be upgraded. The Large Hadron Collider at CERN now is capable of reaching energies of approximately 7 TeV per particle. That equates to accelerating protons to 299,792,455 menorahs apiece, just 3 ms shy of the maximum achievable speed in the universe, the speed of light. At this speed, they circle the ring about 11,000 times per second. If they were traveling around the equator, instead, they would circle the Earth 7.5 times per second. These beams are then made to collide inside several large detectors, the largest of which is as tall as a 7-story building. The collisions are incredible. They occur about 1 billion times per second and generate very hot temperatures, about 100,000 times hotter than the center of the Sun, or 10 times hotter than the center of a supernova, which is the explosion of a star so violent that it can be seen billions of light years away by modern telescopes. Though this sounds scary, each collision actually occurs at a very small scale, smaller than the size of an atom. That's why the equipment doesn't get damaged. But if we want to understand the universe of particles better than we understand them today, are to probe the universe at higher energies and/or at greater precisions, with more collisions than ever before. It's possible to go to higher energies, but the only ways to achieve them are to either increase the physical size of the accelerator, which realistically requires building a new accelerator, or to increase the strength of your bending magnets. It's historically been considered worth it to build a new accelerator when you can increase your energy by a factor of 7 to 10 or more, which is the energy leap that was made from Fermilab's Tevatron to CERN's LHC, and which is the planned leap from the current LHC to the proposed Future Circular Collider, or FCC, the leading prospect for humanity's next particle collider. It's important to plan for that, but also to recognize that it will take more than a decade to construct it. In the meantime, however, the LHC just completed a major part of an enormous upgrade to what's being called the HL-LHC, or High Luminosity LHC. In astrophysics, luminosity refers to how bright an astrophysical source is. In particle physics, it's how luminous, or rich in particles, the beam is. By creating more bunches of particles that collide more frequently, and by increasing the number of particles that collide when two bunches cross each other, the current incarnation of the LHC has already broken the all-time luminosity record for particle colliders. In fact, over the next 10 to 15 years, the LHC will take somewhere between 40 and 50 times as much data as it's cumulatively taken so far, since its first turn-on in 2008. In other words, the LHC data we've collected and analyzed so far represents only about 2% of the total data that the LHC will wind up accumulating. The LHC measures the total amount of collected data in what we call inverse femtobarns, and had collected 150 inverse femtobarns by the close of operations in 2018. The HL-LHC will collect over 250 inverse femtobarns each year when it's complete. With that data, the LHC will be able to test the Standard Model in an unprecedented series of ways. They'll be able to create greater numbers of Higgs bosons than ever before, testing whether it decays according to the Standard Model's predictions to better than Barrier 1 part in 100 precision. They'll be able to test lepton flavor universality, currently one of the 3 still standing Standard Model anomalies, along with the W boson's mass and the muon's anomalous magnetic moment, to unprecedented precision. If it's a real problem with the Standard Model, this will undoubtedly push it over the gold standard 5 sigma threshold. They'll be able to test whether the CDF collaboration's measurement for the W boson's mass matches their value, with much more, albeit less clean data, than Fermilab was ever able to collect. They'll be able to test top quark and bottom quark physics to better precision than ever, either confirming the Standard Model's predictions or running counter to it. And, perhaps most excitingly, they'll look for clues of new physics in places where we might not expect it. With nearly 98% of the total data that the LHC will eventually take left to go, giving up on the possibility that it will find something worth writing home about is both unnecessarily defeatist and also wildly premature. Sure, the expectations of theorists for what might lie beyond the Standard Model have turned out to be abysmal, as all of the scenarios preferred by the community are sorely lacking in any substantial evidence. But the failure of a detective to imagine what clues ought to be there is no excuse for giving up on the case. Yes, it's arguable that theorists have been doing nothing more than stabbing in the dark, and appear to have missed thus far with each and every strike. Yes, the LHC hasn't found a new fundamental particle beyond the Standard Model yet, and it's plausible that it may not, even once 100% of the data has been taken. And yes, there are a number of cracks in the Standard Model, and modern particle physics cannot account for a wide variety of observations concerning our universe. But the successes of particle physics cannot be ignored, and that's a remarkable triumph of the Standard Model, where all of its alternatives fail. In the quest for the next big breakthrough concerning the nature of reality, there's no reason to expect that the fruit we seek will be on the lowest hanging branches. But if we fail to climb the tree of knowledge and see what we discover all the way along our journey to the top, we'll have only ourselves to fault. The game is not yet over, but we can be certain that the surefire losing move is not to play at all. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.